Hey everybody. I hope your weekend was restful and are excited to learn physics this new week. Today we'll have a quick review on apparent weight. We'll discuss friction, it'll be more on friction, discuss more on drag, and more on terminal velocity. All this with the aim of equipping you with more knowledge to attack problems that involve Newton's laws. So, yeah. Apparent weight. What is it? Well, if you remember from last class, I'm going to speed through this section. It's the weight we feel. All right? All right? If the formal definition would be the magnitude of contact forces supporting the object. Yeah. Supporting the object. And the normal force that supports the object in this situation, in the scenario, is the normal force. All right? So it's really the size of the normal force at a particular time. So when is the apparent weight equal to our actual weight? All right, so when is that equal? When an object is in equilibrium. All right? So, yeah, our apparent weight will be equal to our actual weight when an object is in equilibrium. All right, I can show you a quick example. Kind of did not leave space for that, but nice. Okay, I'm just going to go lower to show you. So, if I'm a person and I'm on a surface, yeah, what forces are acting on me? I have my normal force, and then my weight force. The weight pointing my weight, because I have the weight on the surface, I have a normal force. All right, so yeah, this time some more forces in the y direction. Remember, we are moving in the x direction, so we know acceleration is 0. So we got our normal force, we got our weight force, and are we accelerating in the y direction either? No, we're not. So ma is 0. So it's going to be 0. It's going to be equal to n for the weight. Then take the weight across the equal sign. Our weight is equal to n, which is what our scale reads. If we were on a scale, it's initially measuring the normal force that we experience. Okay. So, yeah. Now, what if an elevator is going up? If our elevator is going up, and we still have a similar scenario. I draw my free body diagram. I set my coordinate system already. I'm going to draw my free body diagram. I'm going to do a different color here. I don't know why I began with my normal force drawing it, but I got my weight for sure. It's from going up because I feel more support from the surface because I'm going up. And normal force would be a lot larger. All right. So then the sum of forces in the y direction is going to be the normal force minus our weight. Are we accelerating in the y direction? Yes, we're accelerating. So ma is going to be equal to normal force minus weight. And what the weight we feel, also known as our apparent weight, is going to be the weight plus ma. All right. So this is what we feel. Force normal, if you like, will be your weight plus ma. That's our apparent weight.
If we're going down, same thing. Change the color. If we're going down, same thing. I know I'm moving very fast, but we went through this class. I just want to get to the other stuff so the video is not too long. So, same thing. I didn't even draw my free body diagram. I gotta wait, still there. Because I'm going down, I feel a bit less support from the surface. And yeah, so my normal force is less than my weight. Okay. Am I accelerating? Yes, I am. Normal force, yeah, the net force is down now. So, okay. So, MA, then I take my weight across. It's going to be weight, MA, plus weight. Now, which direction is my acceleration? My acceleration is negative, my net force is negative, so really my equation is, and it's going to be equal to weight minus MA, all right, if you want. And remember, force normal and normal are still the same thing, all right? Just write it in the way that you probably see it in your book. So we feel less weight, so face, that's going to be Fn is equal to W minus MA. Weightlessness, all right? What's going on here? Well, here, as we established, we only have weight on a different color, but let's see, yeah. We only have weight acting on us, so get my free body diagram. Weight. Okay. Yeah, force in the y direction. It's just weight. And what's are we accelerating? Yes, we are. MA. It's going to be mg. All right. Then what direction is our acceleration? It's down, so minus MA. All right. I mean, oops. Yeah, minus. Am I mistaken? Weight's negative. Weight is negative. Then, because we're going down, minus mg. And if I divide by m, what's going on with my Apple Pencil? Okay, it's going to be equal to minus g. And we're in free fall when this happens. All right, so this is a very important concept. There'll be questions about this on your exam. If I zoom out here, you can see the equilibrium, my equilibrium example, the example of the mean up in equilibrium, elevators going up, elevators going down. The big thing here is that the normal force is changing, all right? And when we are weightless, there's no normal force, all right? Because we aren't touching any surface. That's really the main reason why, all right? So now, let's move on to something new. And I'm going to slow down, of course. Friction. All right, let's just do some friction. I know we already talked about friction, but now we're going to talk about it in a bit more detail. So, let's see, what color do I want? I'll go with this orange. I'm liking orange right now. So, what things should I understand from about friction? Zoom in a bit more. Yes. What things should I understand? Friction is everywhere. All right? It's in our shoes, tires, chairs, etc., etc. It basically helps us from, if we didn't have friction, we would just slip away. All right? All right? If we had no friction, we would all just slip and fall. continuously. All right. Continue. So it's everywhere. Now, in physics, it's useful to think about situations where friction does not apply. All right. So when we ignore friction, basically, we just do that for learning purposes. But really, if we look at the real situation, unless we're in a vacuum, we apply friction. All right. And because we're learning about friction today, future models, of course, there'll still be some without friction, but you'll see a lot more with friction as well. So yeah, what is friction? Friction, let's see, what is friction? This is a resistive force that opposes motion. All right, friction opposes motion. That's the first thing you should think about. And what are the two kinds of friction? We got static friction and kinetic friction. All right, so it's kind of like equilibrium, how we have static equilibrium and dynamic equilibrium, but never confuse the two, because I know friction has static friction and kinetic friction. So just be aware of them being of the two definitions and the distinctions, and try not to confuse the two. All right, and here I have a little fill in the gap. Friction always points parallel to the surface. All right, so like the way that the normal force always points perpendicular to the surface, friction is always parallel to the surface. All right, awesome. Okay, let's talk a bit about static friction. Yeah, what is static friction? I feel like changing my color now. Okay, hold on. You know what? I'll just maintain it. Because I want a brighter one. That wasn't as bright. Never mind. All right. What is static friction? See, this is a force. This is a force that exerted by the surface on an object to keep it stationary. How about the right spelling of stationary? Yeah, so static friction, I mean, keeps an object from moving. All right? What direction does kinetic friction point? Kinetic friction points in the direction it would have moved if there was no kinetic friction. All right? So basically, you see at my diagram here. It's not a free body diagram. This is not a free body diagram, just to be clear. I have my person pushing a box, but so in this situation, where would kinetic friction point? Sorry, static friction. I don't know why I'm making that mistake so much. It will point to the left-hand side. All right? So where does it point? Opposite the direction an object is being pushed or pulled. All right? So, yeah. Important notes about static friction. Well, let's analyze this scenario I have over here for a moment. Yeah? Let's see. I have a person here, he's pushing this box, and the box is not moving. Yeah. So let's see. Let's check out this free body diagram. I'm gonna do that right. I'm gonna do that somewhere here. Free body diagram. So you have a normal force. You have a weight force, of course. Weight and normal. And then we have the force of the push. That's true. The force of the push. And then we have static friction. This is how we write static friction, yeah? We have the little f with the subscript s. All right, we have static friction. All right? So one important note about static friction is that it will always adjust itself such that the net force in the horizontal direction is 0. All right? So we're kind of like in an equilibrium a little bit. So if I look at for example, if I have a net force of this size, my static friction will be it would be that same size. So this is my F push, and this is my static friction. But if I have a force of this size, if my static friction will behave likewise and adjust. All right, just trying to keep it steady. All right, so let me analyze my forces. So I know in the y direction, I know they cancel out in the y direction, but because we're not accelerating the y direction, I'm pushing it horizontally. So if I can, I'm just gonna write it I'm gonna write it here. And yeah, f of y is 0, so n minus w. I know my normal force equals my weight. Okay, boom. Now, what matters here is the x direction, because we have something going on. But it's very similar to the y direction, but I just want us to pay attention to what's going on, to see what's going on. Now, friction is in the negative direction, and then my force push is in the positive direction. If I look at my axis. Oops, come on. Okay, yeah. So, what's happening here now is my object is not moving because of static friction. So because my object is not moving, the net force is 0. Okay? Object is not moving. Net force is 0. So 0. So let's see. Let me just write that as a principle. These are the things you should remember when doing these problems. All right. Object not moving in x direction. So x force in x direction is equal to 0. So I got 0. It's going to be equal to minus f of s plus f push. All right. Right now I'm looking at their magnitudes, of course. So really, my frictional force, the static frictional force in magnitude is equal to the force of my push. And just like I showed you here on the important notes, like I showed you there, it's really, that's the behavior of static friction. So now let's answer the question: what's really the magnitude of static friction? If for example, imagine if static friction adjusted to every possible weight, but just imagine if that was the case. It's really not. It's not the case. There's a point at which when we push something, eventually it starts moving horizontally. So we lose the equilibrium. Yeah? So when thinking about the magnitude of static friction, we have to think about it as let's see, as a maximum magnitude, basically. All right. So I'm about to write a formula we haven't seen yet, but the magnitude of static friction. So if I have my F of S and I have my bar say magnitude is less than or equal to mu sub S times the normal force. All right? That's our magnitude of static friction. So, mu is just a Greek sign. It's a coefficient. It's a coefficient of static. It's the coefficient of static friction. All right? This number depends on the two surfaces that are in contact during an interaction. Like, for example, if we have a block on an inclined plane, what's the material of the inclined plane? What's the material of the block? All right? So the coefficient would tell us, the coefficient will basically tell us how much static friction is in between those two materials. All right? So, yeah, how would I describe mu sub S? Let's see. Okay, so first of all, mu sub S is a constant. It's a constant, yeah? And it depends on the material of the two surfaces, in contact. All right. So if I go back to my box example, I have my box here. Let's say my box is made of rubber, and my surface, is made of wood. I really want to close this gap. I don't think I'll be successful, but let's see. Okay, that's good enough. All right. The value of mu sub S really is something that's given to us experimentally. It's going to be 1.00. All right. The values of mu sub S will be given to you in your exams. If it's not given to you, you can solve for it by manipulating this formula. Like if you know the static friction, if you know the static friction and the normal force, you can just say you find mu sub S by dividing the magnitude of static friction by the normal force. All right, and that should give you mu sub S. And my box doesn't have a cap. All right. So I hope that gives you an idea. So when we're doing our force problems, really, when we have static friction, we're thinking about mu S times the normal force. And we'll talk about y is proportional to the normal force a bit later in the video. Kinetic friction. Oh my God. Can I zoom out? All right, sure. All right. So, imagine our box. Remember our box example? Yeah, our box was stuck for a very, very long time. Yeah? But now we've actually got it to move. Boom. So once our box gets out, surpasses the maximum magnitude of static friction, we get into kinetic friction. All right? After that, we get into kinetic friction. All right? So, what is kinetic friction? Kinetic friction is basically
friction that occurs whilst an object is moving. All right, let's see. Friction that occurs when a box is moving. All right, so if I have my and let's see, what does it point? It always points opposite motion. Opposite to the motion. Like my object will, if my object is moving to the left, it will point to the right. My object is moving to the right, friction will point to the left. If my object is moving down a ramp, friction will point up the ramp. All right. So yeah, let me just give you a little example here. Oh my God, box. Thank you. I want to move this thing. Okay, imagine. Hold on. All right, great. Now, nice, great. So my box is moving. So I got it's moving. This and something's moving has a velocity, of course. It's moving. So that means my friction, my kinetic friction, will point that way. All right. So now, what's the magnitude of kinetic friction? Well, I want you to think of kinetic friction as something that's kind of almost an ever-present, really. So it's not really like there's no cap through which we don't have kinetic friction. So really, we don't need the greater than or equal to sign or less than or equal to sign. So the magnitude of kinetic friction, I would say, is u sub k times n. All right, same idea. All right, mu sub k, because mu sub s for static friction, mu sub k is the kinetic friction coefficient. All right, and then n is the normal force. All right, n is just the normal force, and normal force magnitude. All right, so this tells us, and similar to static friction, it tells us how much friction exists between two surfaces in contact. All right, so that's mu sub k. All right, some important things to know about mu sub s and mu sub k. One thing. So number one, mu sub k will always be less than mu sub s. All right, and why is that so? Well, the amount of force needed to move an object that is already stationary, that is stationary, is less than the amount of force needed to keep an object moving. All right? So, because of that reason, mu sub k will always be less than, that's an example to show us that mu sub k is less than mu sub s. All right? That's an example. So, mu sub k is less than mu sub s always. All right? And remember, we're talking about friction between two surfaces. So we have a few experimentally verified values of this mu sub k value. So if I have a value of mu sub s here, then I have a mu sub k. All right. So let's say if I have rubber, the material rubber moving on wood, its the static coefficient would be 1.00, and the static coefficient, and the kinetic coefficient, the kinetic friction coefficient will be 0.7. All right. What about rubber on wet concrete? Rubber on wet concrete. Static friction 0.7, and of course it will easily move whilst it's moving fast, while it's already moving, so there'll be less friction. It'll be 0.5. All right. And then let's see, one more. Shoes on wood. Shoes on wood. The frictional coefficient, the static coefficient is 0.9, and the kinetic friction coefficient is 0.7. So just showing you these values are verified in the lab. People are doing a lot of things to get these values. You never have to derive mu sub s. Don't worry about that. All you can do is just manipulate the equations that I've given you here, or most likely though in the exam they'll just give you mu sub k or mu sub s, and then you have to solve a particular problem involving friction. All right, let's move. Some problems. All right. Let's see. Earl, so we have some problems here. Earl wants to move his 32 kg sofa to a different room. All right. He puts his sofa sliders. So like here's the sofa. Because he wants to move the sofa, he puts sofa sliders under the sofa. These basically help move the sofa easier. And they have a kinetic friction coefficient 0.80. And then pushes the sofa at a steady 0.4 meters per second across the floor. How much force does he apply to the sofa? Okay, so this is the drawing. This is an example from your book. So you have our coordinate system and my free body diagram. It's gonna be here. You have the normal force and the weight. Because I'm on the surface, I have the normal force. And then now I got the force of the push. So now I'm moving in constant velocity. All right? Like notice here I say I have a steady push. I move at a steady, like I'm not changing my speed. My speed is staying around at a steady 0.4 meters per second. So we are kind of in a dynamic equilibrium. All right? We're in a dynamic equilibrium. So the y direction cancels out. We know that. So we're going to only focus on the x direction. And the y direction cancels out because we're not accelerating in the y direction. So if I look at my x direction, all right, let's see, to be neat, so I will put the positives first. So let's see, my positive vector in the x direction, push, the force of my push, minus my frictional coefficient. All right. So now let me get the magnitudes of these forces.
Let's see. What's the force of my push? Well, hang on. Am I mistaken? Well, anyway, sorry, apologies. Because we're in a dynamic equilibrium, f of x is going to be 0. All right? Okay. All right. We are moving at a steady, these are the words, 0.4 meters per second. We are in constant velocity. All right? So f of x, the sum of forces in the x direction will be 0. So we want to know how much force is he applied to the sofa. So that's F push, all right, our force push. So now let me get the magnitudes. Let me change. Let me move our kinetic friction across the equal sign goes to F push. So now I see my kinetic friction is equal to F push, which is okay. This is what the dynamic equilibrium predicts. All right. So now, what's the magnitude of the kinetic friction? Yeah, we've solved. We have it in vector form, but we need to get it. We need to know the actual size of the force. So we saw that kinetic friction is going to be equal to mu k times the normal force. Yeah. So F push is equal to mu k times the normal force. Yeah? So, we are given the mu k in the question. Our mu k is 0.080. And what's our normal force? Our normal force, well, our normal force is, that's easy. We have our mass. Normal force is just mg, because if we have our weight points down at minus mg. Our normal force points up at mg. They're equal and opposite. But remember, they're not a third law force. They are not a third law force. The normal force and weight are not a third law force. Anyway, so just wanted to be clear on that one. So our normal force is mg in this case. So really the magnitude of our force push is going to be mu sub k m times g F push. So the physics is done. So now just get a calculator. Yeah, make sure they're all in SI units so you can get a good Newton. And by the way, the mu sub k and mu sub s are dimensionless coefficients, all right? Mu sub k and mu sub s are dimensionless, meaning they have no units. All right, then g is going to be 9.8, all right, meters per second squared. And when you put in the calculator, I'm not gonna do that, but that's your F push, all right? I've taught you the physics is there. Now you can do math. All of you can do math. You're in AP Physics, so yeah. So now, let's do one more problem. Earl is back outside, yeah? Our Earl is back outside. Earl the penguin. I hope you remember. I hope you guys remember Earl. So he's back outside. Yeah? He's gliding down a snowy slope. Find the coefficient of kinetic friction oh my god, why did I say this skier? Sorry, I made this while I was tired. For Earl, if the friction is known to be 45 newtons. All right, we've solved the problem like this before. We have. So, we're going to be a bit quick. Remember our coordinate system, we align it, and this is theta is 25 degrees. We'll align our coordinate system with the slope, y, x over there, and our normal force. So this is our coordinate system, yeah? Positive y and positive x, yeah? And let me change it. Let's get our free body diagram going. FPD. Change the color a little bit. So we have our normal force perpendicular to the surface. All right. And we have our weight force pointing down, straight down. All right. And if this breaks, we break it into its components. We have, let me change color for the weight, for the vectors. You're gonna have our weight x over there and our weight y there. And then this one right here is just our weight, and that's our normal force, all right? And because of trigonometry that I've shown you guys before, which I hope you remember now, that's our theta. That's where theta is, all right? And O'Reilly just joined the Discord. Awesome. Okay, so now this weight x is the line that connects wy to w. So because the vectors, they can just move around. We can just move them around, really. Wx ends up over there. So, yeah. This is our coordinate system. Oh, I kind of like my omega y to be straight, to be a straight line with the normal force, because that's how it is truly. So yeah, good enough. Oops. All right, apologies guys. I did unnecessary minutes to the video. Okay, so here's our free body diagram. All right, now we have our free body diagram. Let's do some math. So the forces in the x direction, let's see, we have a kinetic. We have in vector form. We have weight x in the positive direction. All right. Oop, I forgot my friction. I got friction over there. Kinetic friction. So F sub k. So on the negative direction, I have my kinetic friction. All right. And those are in vector form, of course. And in the y direction, I don't have any motion. I'm just gonna put that there for learning purposes. The normal force minus my omega y. All right. So now, let's see. My question: did I have this guy moving at a constant speed or not? No, it's not. Okay. So now, what's omega x? Omega x is something we can find with our triangle here. This right here, remember I told you is omega x. This vector that connects omega and omega x is omega x right here. It's given by sine theta. Sine theta is our adjacent of our hypotenuse. So really, which was our adjacent angle? omega y. What? Over. Okay. It's interesting. Just go with it unless I'm tripping. I thought it would be different. Apologies, guys. I'm just trying to see something. This is weird. Let's see. I feel my theta right here. So my adjacent is going to be omega y. That is true. My hypotenuse is A. And that's because I used the wrong abbreviation. Oh my God. See, even with for a 4-year physics degree, I still make this mistake. So if you make a mistake, don't beat yourself down. So long as you can identify your mistakes, you'll be fine. So SOHCAHTOA is the opposite of a hypotenuse. So there we go. Now, so my sine theta is the opposite angle over the hypotenuse. So then, now, to get omega x, or at least the magnitude of omega x, I have omega sine theta. I cross multiply, and my omega x goes multiplied by 1, and my sine theta multiplies by omega. And my wx is, my omega x is omega sine theta. All right? So, I'm not going to do it for the y direction because we are not moving in the y direction. We don't care about the y direction as much. I mean, we do, but actually apologies. I will do something for the y direction. Apologies. I'm making a lot of mistakes here. I'm sorry. Anyway, let's move. So, if I put them in their magnitude form now, all right, f of x is going to be equal to w sine theta minus mu sub k. It's going to be the normal force. It's going to be n. Now, what's the normal force? What's our normal force? We need to find that out really quick. Our normal force, well, f of y is 0. So let me put it right over here. Sum of forces in the y direction is 0. And then our normal force is technically n minus, then we're subtracting the weight. If we take the weight across, the equal sign is going to be weight. Our weight, the y component of our weight, not our weight. So the y component of our weight is now equal to the normal force. So now what's the y component of our weight? How do we find that? We decompose. Same thing. Right over there. Cosine theta. All right? Cosine theta will help us find the y. And that's C A H. So the adjacent angle is omega y, and the hypotenuse is omega. So cross multiply. Omega y is equal to omega cos theta. So now, okay, omega cos theta. Okay, so now we know the value of n. We know the value of our normal force. And we got the normal force from solving the equation in the y direction. We can now plug it in to our x direction. So let's see. We'll make it a bit bigger. Up here following. So sum of forces in the. So let's see. We know the value of friction. Hold on. So we know our normal force. Apologies. I think I may have done too much for this problem. So let's see. We know our friction. Our friction is 45 newtons. Yeah? And what else do we know? we now know our normal force. Our normal force is omega cos theta. All right? So we want to know mu sub k. Well, our equation for mu sub k, or at least for kinetic friction, is f of k is equal to mu sub k times n. So if I divide by n, it's going to be equal to mu sub k f of k over n. All right, and it's going to be 45 over w cos theta. I see. And then w, or omega if you like, is just mg. So mg cos, now theta is 25. It's going to be equal to mu sub k. So, and that's, we know the mass. Do we know the mass? Let's see, do we know the mass? The mass is 62 kg. All right? Arrow is 62 kg. So, m equals 62, g equals 9.8. And all of this can be put in a calculator, and from there, you can easily find mu sub k. I know it's a bit rough. I apologize for the mistakes I made, but really the actual sense for this problem, we didn't really need the x direction. Actually, we needed the y direction to get the normal force, and the normal force gave us the friction, the kinetic friction. Interesting. Don't worry, we'll clear it up in class if you're not too confident on this. Okay. So now I'm telling you that friction is proportional to the normal force. Why is that? Okay, so when two surfaces are in contact, right? Let's say this is surface one. And then I have surface 2, a different color. Surface 2. Alright? At the microscopic level, this is how they connect. Alright? From a macroscopic level, to the level our eyes can see, we see a very smooth connection. All right? We see a very smooth connection, what we see. But really, on a macroscopic level, this is how it looks like. All right? So, when two surfaces are in contact, on the microscopic level, actually only 0.1% of surface area is actually in contact. It's actually touching, which is crazy, all right? And this right here is the 0.1%. That contact, the actual contact is 0.1%, all right? So it is those contact points that cause friction, yeah? So now, the normal force comes in because the stronger we compress surface 1 and surface 2, the more contact points we'll make, all right? So the stronger surface 1 and surface 2, or let's say the stronger surface 1 is compressed on surface 2, the more friction we have. All right? So because my normal force is basically the weight force
but in the opposite direction. The stronger I compress a box, I am kind of, in a way, adding to the forces in the y direction over there. So, yeah. So, yeah. Because my weight, because the forces in the y direction are a lot more, like in the negative y direction, sorry, my normal force will also increase. So that's why friction is directly proportional to the normal force. Because on the microscopic level, we are getting more contact points, and more contact points between two surfaces is more friction. You get what I'm saying? So yeah. And when we move, when we move from static friction to kinetic friction, like when we're finally able to move an object after pushing it, we go through the contact points go through multiple collisions with other high points, with other contact points, and that's the summary. That's really a summary of why this is moving like that. So yeah. Anyway, please watch part 2. Part 2 is on drag. It's very, very important for tomorrow's class. So yeah, ciao for now.